You've studied the three states of matter plenty of times before. In this unit, we're going to focus on the condensed states of matter, solids and liquids. We studied gases in some detail in Unit 2 this year. Remember the kinetic theory of gases? Kinetic theory says that gases are composed of small, hard spheres of insignificant volume. That means the majority of the gas sample is actually empty space. Kinetic theory says there are no forces of attraction or repulsion between particles. The particles are in continuous, rapid, random, straight-line motion. Any collisions between particles or between gas particles and a surface, any collisions at all, are considered to be perfectly elastic, meaning that no energy is lost during the collision. Finally, kinetic theory states that the average kinetic energy of particles is directly related to the Kelvin temperature of the sample. When comparing solids and liquids, the condensed states of matter, to gases, the structural difference should be clear. In the condensed states, the particles are very close together, while the particles of a gas are spaced very far apart. This gives rise to noticeably different macroscopic properties. While gases have low densities, solids and liquids are much more dense. The density of a gas is affected by temperature. As temperature decreases, for example, the particles slow down. They pack closer together. Smaller volume means higher density. Solid particles are already so close together that a temperature change doesn't affect the particle packing. For the same reason, the fact that the particles are already very close together, solids are incompressible. Liquids are said to be virtually incompressible. If you compress a liquid to any extent, you're going to push the particles closer together until the sample becomes a solid. In comparison to the condensed states, gases are highly compressible. There's lots of space between gas particles, so those particles can be pushed together quite a bit, and the sample still remains as a gas. Finally, solids have a rigid shape and volume. Liquids have a definite volume but conform to the shape of their container. Gas particles spread out and take both the shape and the volume of their container. Hopefully you're seeing that there's a real separation between the condensed states of matter and the gaseous state. The question is, what causes this difference? The answer is interparticle attractions. These are the attractions, the forces that hold one particle close to other particles in the condensed states. According to kinetic theory, these forces of attraction do not exist in gases. The strength of these interparticle attractions affects the physical properties of the substance. For example, the stronger the interparticle attractions, the higher the melting point. Why would that be true? If the force holding the particles close together is strong, it'll take more energy to weaken that force so the particles can spread out enough to become a liquid. More energy needed means a higher temperature required. What do you think would be true of the boiling point for a substance with strong interparticle attractions? The stronger the attractions, the higher the boiling point, for the same reasons as before. For a liquid to become a gas, the particles must be separated, completely separated. All the interparticle attractions must be broken. If the interparticle attractions are strong, it will require more energy, a higher temperature, for the force to be broken. Viscosity. is another property affected by the strength of interparticle attractions. Viscosity is a liquid's resistance to flow. Syrup is viscous, water is not. The stronger the interparticle attractions, the higher the viscosity. Types of interparticle attractions, and we'll discuss all of these, include ionic bonding, the Coulombic attraction between cations and anions. Sometimes, rarely, covalent bonding is not only the force inside a molecule, but a force between molecules as well. I'll talk more about that in the video about crystal types. Metallic bonding, the attraction between metal ions and their sea of valence electrons, is an interparticle attraction. And then we have a group of particle attractions called intermolecular forces. Intermolecular forces exist between molecules. These are attractions between one molecule and another, not the covalent bonds inside an individual molecule. For example, we're not talking about the covalent bond between a hydrogen atom and a chlorine atom. That's inside the molecule. We're looking at forces of attraction between molecules, a force between one whole molecule and another, not the bonds inside each molecule. Also, these are molecular forces, so they do not exist in ionic compounds or metals. All types of IMFs are based on the distribution and interaction of charges, partial charges, or temporary charges. That means these interactions are governed by Coulomb's law. Remember, Coulomb's law says that with greater distance apart, the force decreases. Also understand that with increasing temperature, particles are moving faster. They're spacing themselves further apart. So again, the IMF strength decreases. This is true for all types of IMFs. In all cases, intermolecular forces are weaker than the intramolecular covalent bonds within the molecule. This is an easy fact to observe. What happens when you add heat to water? It boils. Liquid water becomes water vapor. Did you change the internal composition of the water molecules? Nope. Every water molecule is still intact. You broke all the IMFs between all the water molecules. So the water molecules are no longer close together in liquid form. You did nothing to the covalent bonds between the hydrogens and the oxygens. During any phase change, the molecules stay intact. The energy is used to separate the molecules from one another. In other words, the energy is used to overcome the intermolecular forces between the molecules. There are three main types of intermolecular forces you must know: dipole-dipole forces, hydrogen bonding, and London dispersion forces. Additionally, there are a few mixes that we will learn about as well: ion dipole forces and dipole-induced dipole forces. Recall from our previous unit that dipole is another word for polar. Dipole-dipole forces are the forces between polar molecules. The positive end of one molecule feels an attraction to the negative end of an adjacent molecule. This attraction is about 1% as strong as a covalent bond. Of course, in an actual sample, things are a bit more complicated than this picture. There are both attractive and repulsive forces occurring, but on the whole, the attractive forces dominate. Hydrogen bonding is another type of intermolecular force. When hydrogen is covalently bound to a nitrogen, oxygen, or fluorine, like in water, as an example, the resulting bond is extremely polar, with the hydrogen end positive and the other end negative. The attraction with another molecule, then, is very strong. The reason nitrogen, oxygen, and fluorine get the job done is because they are very electronegative and very small. That's what makes the covalent bonds to hydrogen so very polar. Very polar bonds means very polar molecules, which means a very strong attraction. Hydrogen bonding is an especially strong dipole-dipole force. Be careful with your vocabulary when you discuss hydrogen bonding. A common mistake is to say something like, the hydrogen covalently bound to an NO or F is a hydrogen bond. That's wrong. When H is covalently bound to NO or F, it results in a very polar molecule, which then can undergo hydrogen bonding with another molecule. As we've just seen, hydrogen bonding occurs between water molecules. Molecules of ammonia also attract one another via hydrogen bonding. The electropositive hydrogen end of one molecule is attracted to the electronegative nitrogen end of another molecule. One common misconception about hydrogen bonding is that it can only occur between two identical molecules. In truth, so long as hydrogen is covalently bound to NO or F in a molecule, it can undergo hydrogen bonding with an NO or F on a nearby molecule. For example, the electropositive hydrogen end of a water molecule can attract the electronegative nitrogen end of a molecule of ammonia. This type of hydrogen bonding, the bonding between different types of particles, is what holds the base pairs of DNA together. Looking more closely, here, hydrogen is covalently bound to a nitrogen on one base pair, and then undergoes hydrogen bonding to an oxygen on an adjacent base pair. Again, hydrogen is covalently bonded to one atom and hydrogen bonded to another. You don't have to have hydrogen bound to nitrogen, oxygen, or fluorine covalently in both molecules involved. Another example of hydrogen bonding is the polymer nylon. One long polymer chain is attracted to the next via hydrogen bonding. The two types of IMFs we've discussed so far, dipole forces and hydrogen bonding, occur between polar molecules. It's pretty easy to understand that polar molecules would attract each other. Polar molecules have positive and negative ends. They're like little magnets, with their positive and negative ends attracting one another. But how could nonpolar particles, iodine molecules, carbon dioxide molecules, how could they ever attract one another? Nonpolar molecules and atoms must be able to exert forces on each other, otherwise these substances could never be liquid or solid state. Solid carbon dioxide, dry ice, most definitely exists. The third type of IMF, the only force that can occur between nonpolar particles, is called London dispersion forces. Here's how it works. Imagine a nonpolar particle as a uniform cloud of evenly distributed electrons. Visualize those electrons moving. At any given moment, the electrons aren't evenly distributed. They get bunched up in one area of the electron cloud. Another area doesn't have any electrons. Think students moving through the halls during class changes. You get all bunched up. So when electrons get bunched up in one area of a particle's electron cloud, that particle for just a moment is polar. That's called an instantaneous dipole. This then affects the electrons in the next particle over. The electron-rich section of particle A pushes away the electrons from the adjoining region of the cloud of particle B. This is called an induced dipole. For just a moment, both particles are polar, and so they attract each other. Because these particles are not polar at all times, they're only polar for fleeting moments, dispersion forces are typically pretty weak. The lower the temperature gets, the slower the electrons move, the longer the temporary polarity lasts, and the stronger the dispersion forces. When the temperature gets low enough, the particles pull close together and a change of state occurs. As the temperature decreases and molecular motion slows, the IMFs can pull the particles closer together, resulting in solidification of a liquid or condensation of a gas. There is great variability in the strength of dispersion forces, but in general, dispersion forces are weaker than the other types of forces that can occur between molecules. As we saw on the previous slide, dispersion forces exist due to the movement of electrons. When electrons zip around in the particle's electron cloud, they get bunched up. Which is more likely to get bunched up? A small number of electrons or lots of electrons? When are you going to get caught up in the halls? When you go to the bathroom during class, or when everyone is in the halls during a class change? It makes sense that the more electrons in a particle, the more likely they'll get bunched up. This concept is called polarizability. More electrons means more polarizable. More polarizable means a stronger attraction between the particles. Here's an example question. Predict which molecules would display stronger dispersion forces. A sample of little 2-electron hydrogen molecules, or a sample of 106 electrons each iodine molecules. The answer is definitely iodine. Why? Because of polarizability. Because iodine has more electrons, it is more polarizable, meaning the dispersion forces between iodine molecules is stronger. In addition to polarizability, the strength of dispersion forces is also related to the shape of the molecule. Consider N-pentane and neopentane. These molecules are isomers. That means they have the same molecular formula but different chemical structures. Same molecular formula means same number of electrons. So why the near 30-degree difference in their boiling points? The difference is in the shape of the molecules. N-pentane is long and straight. Neopentane is roundish. Which would touch in more places? 2 long, straight pencils or 2 bouncy balls? The long, straight N-pentane molecules can interact over more area than the roundish neopentane molecules. Therefore, the attractions between N-pentane molecules are stronger, and the boiling point is higher. Let's summarize the three intermolecular forces we've talked about. Which type of IMF is typically weakest? Dispersion forces. Where can dispersion forces come to exist? Dispersion forces exist between any molecules or atoms that have electrons. That's all of them, by the way. A common misconception is that dispersion forces only exist between nonpolar particles. That's wrong. Dispersion forces, it's true, are the only IMFs possible for nonpolar particles. But all molecules and atoms exhibit dispersion forces between one another. Anything with electrons will have dispersion forces. What IMF type is in the middle in terms of strength? Dipole-dipole forces. Where do these occur? Between polar molecules. And finally, what is the strongest type of IMF? Hydrogen bonding. And what are the conditions required for hydrogen bonding to occur? The molecule must contain hydrogen covalently bound to a nitrogen, oxygen, or fluorine. That molecule is then capable of experiencing hydrogen bonding with another molecule. By now, you might have lost sight of why we started discussing IMFs in the first place. The forces of attraction between particles affect the macroscopic properties of the substance. Properties like the melting point and the boiling point of the material, and therefore its physical state of matter at a given temperature. Types of particle attractions and their strengths affect a material's ability to conduct electricity or heat, its chemical reactivity, its hardness or softness, plus a lot of other properties. An understanding of a substance's inner particle attractions helps us to understand and predict macroscopic behaviors.